Okay, so let me start by acknowledging the people. So this is the lab at Campus Biotech. I know we should do a new lab picture. So this is I could also call it the floating heads lab because I need to add on too many heads. We'll do that soon. But there is a subgroup of people I like to thank especially, which I call the graph signal processing team. And so there is Giulia, Preti, Rafael, Toma, Anjali, Milan, Elvira, and then also we work also in collaboration with Hamid, who's in Sweden at Lund University. And of course there is one person I particularly like to highlight, which is Thomas, who will be the master brain hacker today. He's sitting in the front, but he will come back in a moment. And so he will be the one who guides you to all the practicalities of putting graph signal processing in action for neuroimaging. So, well, when he's back, let's thank him in particular, because he really took care of this session from the beginning to the end. Okay, so let me quickly start again. So MRI, great machine, we can do structural information, and I will go very quick on this one because Matteo's talk was more than sufficient on this. But of course, to summarize, you can do standard structural images, which give you excellent tissue contrast. You can see gray matter, white matter, CSF, and so on. And so we also know, of course, that the gray matter can be segmented. There are various ways of doing that. And you can come up with anatomical atlases based on these structural features. So here you see just one example, it's just for illustration purposes. And then, of course, with diffusion-weighted MRI, you can probe within the white matter, because within the white matter is where the axons lie. And since they basically aggregate, come together in big bundles, and the diffusion is more or less restricted depending on the orientation of these bundles, you will become sensitive to their orientation if you do diffusion-weighted images sensitized to different orientations in 3D. So again, Matteo explained you all the details, but if you go to different orientations of a diffusion-weighted sequence, you will see that the signal changes, and this depends on these local orientations in the white matter. And all this can be summarized in computational models. One simple way, historical, to do this is tensor imaging, where you basically fit this three-dimensional ellipsoid to your measurements, or you can go to more complicated models that take into account that you can have basically multiple ellipsoids in a single voxel. And then based on that, you can do tractography, you can do it deterministically, probabilistically, many variations, to get these very beautiful virtual reconstructions of the tracts, or let's say the white matter fibers, as we also call them. And this can be compared to histology. Again, Matteo showed you all the details of this. Now, the essence for my talk is that thanks to diffusion-weighted MRI, you can do whole brain tractography, and you can summarize this into a structural connector, which is basically a graph model of structural connectivity. So you associate nodes to brain regions in the gray matter, and you have your edges, and the edge weights are given by a feature of structural connectivity, which could be number of streamlines or things like that. And so that defines the wiring diagram of the brain, right? And in the end, at the graph model level, it's basically an adjacency matrix that gives you, between any pair of regions, a strength of structural connectivity. Okay, so that's what I just said. Now, once you have defined a graph, you can start playing with graph theory. And that means that you could, of course, visualize things to start with. And what you see here are your nodes projected on in the brain view. So the locations of the nodes are given in XYZ in the anatomical brain. And for instance, the size of the spheres here are modulated by the degree of each node, which is the sum of the weights of the connections that go to that node. And you can already appreciate, for instance, here, this from a structural connectome, that you have very strong anterior-posterior connections, for instance, especially at the medial, at the midline. Now, the great thing of graph theory is that you can also produce so-called topological views. So you can look at, given the connectivity that I have captured in my adjacency matrix, or there are other more informative ways of visualizing these nodes, such that I might discover organization that is not obvious to recognize from the brain view. And this is basically related to graph clustering and community detection and those type of topics. But as you can see here, if you would reorganize the nodes in a topological view by some mathematical criterion, and you would observe something like this, it's clear that you can recognize different clusters. And these different clusters will group together brain regions that are in the physical space not necessarily very close. Okay? But in the connection space, they might be very much related and so become very close in the topological view. And then you could, for instance, discover communities or modules, and this might be interpreted from a neuroscience point of view that the intramodular connections, so the ones that run within these clusters, they basically support common functionality, and the intermodular connections, they basically, well, they need to go through hub nodes, which might be the ones here in purple, which are the ones that within the module are mostly responsible for getting outside of the module, and so they would facilitate communication. I'm just giving one example of many possible types of organizational principles you might want to discover out of this type of visualization. Okay, so that's structural, and now let's go to functional. I think you didn't see a lot of fMRI yet, or even nothing so far. Did you already have some fMRI in the Brainhack? Yes? Also? No? Okay.
Today's the fMRI day.
Today is the fMRI day. Okay, so then, okay, let me start at the beginning then. So this is an artistic rendering of the brain, the living brain. So what do you see here? You see vasculature, and you see blood flowing through. And actually the brain is heavily, how would I say, irrigated by the blood vessel system for the very reason it needs it, right? It needs to have red blood cells bringing in new energy for the metabolism, which it needs very much because it consumes about 20% of your energy budget. So one of the fundamental insights is that there is this phenomenon of neurovascular coupling, which means that if you have, let's say, intense activity of neurons in the vicinity of this place in the brain, what will happen is a coupling, an induction, if you like, in a change of blood perfusion due to the neural activity that will lead to a so-called blood oxygenation level dependent signal, which can be detected through various mechanisms with the MR scanner, by MR physics, basically. And so one of the characteristic features is that the signal change will be very, very slow. So it takes 4 to 6 seconds before, even if you only had like 200 milliseconds of intense neural activity looking at the flashing checkerboard, it will take 4 to 6 seconds before you really get to the peak of the signal. And then it takes a very long time, like let's say 12, 15 seconds before you get back to baseline. And this is called the hemodynamic response function. And this is what we can measure with fMRI. Now, one thing to acknowledge is that actually the initial consumption of oxygen that happens during the 200 milliseconds, or very closely to it, you can actually not measure. It's also called the initial dip, and there are people dedicating their career of finding it, and it's very elusive. And it's even debated if you can really measure it, but that's another topic. So what you do measure is an overcompensation of the system. So basically the biology is built to, have the worst case scenario. So you have the neural activity And then the neurovascular coupling says, okay, let's bring new blood in there, and if it's too much, it's not a big problem. Okay. And so that's why we actually, thanks to nature, we actually get a big signal. Otherwise, we probably would not be able to do fMRI at all. And yeah, let me also mention Angelo Mosso, because Sir Charrington is, of course, very known for neurovascular coupling. But before him, there was this Italian neurophysiologist from Torino. and he did wonderful experiments in human. He had this human circulation balance. I won't go too long into it, but which is a fantastic thing. You need to Google it. And so basically, he was looking how the blood redistributes in humans as he exposes them to a cognitive paradigm. Okay, he was basically talking to them how beautiful their wife is, and then the subject, well, tilted, and so on. I mean, you need to look at it. Okay, but since then, we have MR, and we can do this fantastic scanning. And so here you see a kind of a basic visualization of how just resting state fMRI looks like if I do some minimal pre-processing, which means I remove the baseline, such that 0 becomes baseline, and red is an increase with respect to baseline, and blue is a decrease. Then I have all the axial slices from ventral to dorsal, and I accelerate 4 times the whole movie, because otherwise it's a bit too slow and too boring. And as you can see, it is dynamic, right? I mean, the subject is doing nothing. So, and if you look long enough at this, you can really recognize patterns and homologous regions that activate at the same time, etc., etc. So the structure is kind of obvious that there is things going on, and it's not just noise. Now, one of the standard ways of trying to build network models, graph models out of functional information, is to look at pairs of activity. Well, to map this first into an atlas again. And then you have a time course now that is associated to each brain region of your atlas. And then you compute functional connectivity, which is typically just Pearson correlation between those time courses. So between all pairs you can get, you compute Pearson correlation, and you put it all together again in an adjacency matrix, and we can call this the communication diagram. Okay, it's another graph model. It summarizes all the functional information, and as you can see, it is, if you remember from the structural connectome, this one is actually much more dense, which makes sense because if you have indirect connections, they will still have high connectivity here, while of course if it's an indirect connection structurally, you only have the direct connections in that diagram. And this has been used since many years, now more than 10 years, to analyze functional organization again, to discover organizational principles and so on. And let me just show one example, which I always found very beautiful, like 10 years ago. So where they looked at functional connectomes, and they visualized them with a nice method of visualization. It's basically a topological view, so acknowledging for connectivity, and then putting the nodes onto a two-dimensional plane. And so this was a study where they looked, it's a developmental study, so they looked at subjects starting from the age of 7, and I will start the movie, and you will see how in the topological view, the functional organization will evolve up to the age of 23, I think. So there we go. So in the beginning, voila, there we go. So now we have, oh, I'm sorry for that. Let's start again. Yes. Okay, so 8, 9, etc. So it goes up. I don't know if you can see it. And so here you see the legend. So you have the different lobes over here, and these are actually functional networks. And so the main feature you need to recognize is as you get to the age of 16, 17, everything becomes much more integrated than in the beginning, right? So as we develop, at least the functional integration is tremendously increasing, and some nodes that were at the periphery of the topological view are now really in the middle of it. So it's really a matter of, at least from the communication diagram point of view, of integrating things much better as you get older. And now we are at the age of 26 here at the end. So just one example. Okay, so now the problem, the challenge, and the reason of the brain hack. So although there have been many attempts to link structure and function, because we can build structural networks, we can build functional networks, and so obviously, I mean, how do they relate, right? And one family of methods is to look at correlation between functional and structural connectivity. And this has been done. I think this is the paper by Honey, one of the first ones trying that. Obviously, it kind of gives a positive trend, I mean, as expected, where you have strong structural connectivity, you have a high probability of large functional connectivity, and the inverse. But as you can see, it's a very blurry scatter plot, right? And it doesn't really explain you how and why and so on. You can go with more focused hypothesis, and you can say, okay, let's identify a few regions out of, let's say, an fMRI study, could be task fMRI, because those are the ones I like to really know how they communicate functionally, and then also, once you have established them, you do structural connectivity between them. Okay, so you could then look at what are now the structural connections supporting these communications in that small network that I have identified from fMRI. So I call this functionally guided structural analysis. And then you have another class of methods, which I will refer to as brain simulation approaches, like the virtual brain and others, where starting from a structural connectome, you put on the nodes some models of basically neural oscillators of how brain activity at the nodal level can be generated, and then how it can be influenced given the connectivity of those nodes by the oscillations in other places in the brain. And you let this thing run and simulate, and you can convolve it with an HRF, and you can have this type of simulated functional connectomes, etc. And so that's another type of method. And so, well, I think none of these is really good, so I propose yet another one. And so what I will propose is, no surprise, graph signal processing. And I think it's new. That's always nice. So everything you do is new. So then, I mean, it's not a matter of doing better. Yeah, it's easy to publish, but that's not the only reason. I think it's a fresh way of trying to combine structure and function. And I hope I convince you when it becomes concrete. So because it really integrates both at the level, at the place which structural connectivity deserves, and the place which functional information deserves. And as you will see, functional information will not be summarized in functional connectivity. It will remain at the activity time course level. And I think that is, in a way, a better way to combine both, instead of summarizing and then trying to look at correlations and things like that. Okay, let's try to get a little bit concrete. So when we are introducing the graph signal processing framework, already, of course, in our head, with applying it to this brain imaging application. So we will assume that we have a structural connectome as the graph model. And that means we have a symmetric, undirected graph, directed weighted graph, so it's characterized by symmetric adjacency matrix, which is n by n, and regions, which I refer to as the matrix A. And then the degree matrix is a diagonal matrix that just has the degrees of each node on the diagonal elements. And the one we have taken is extracted by from the Human Connectome project, 100 and a bit healthy individuals. And we're using the Glazer's multimodal atlas, 360 regions. And then we used a fairly standard but state-of-the-art pipeline to construct the structural connectivity, and to average this across all subjects to have a kind of a stable, group-level, generic structural connector, which you can see over here in logarithmic scale. So that's the graph model. If you say graph signal processing, there needs to be a graph signal also. And that's the novelty with respect to graph theory in general. And the graph signal will be the fMRI signal. So it's basically, if this is the representation of my fMRI data, which could be resting state or task or whatever, it has been summarized in regional averages at the spatial level, but basically in every column of this matrix, you have what I call a graph signal. So for each time point, you will have a vector of length n that is the activity measured at that time point in these different regions. Okay? So this is very important. That's the concept. Okay, so now the next important step, at least for the type of GSP we want to do. So we will introduce a concept of a graph Fourier transform. And who knows a graph Fourier transform? Who knows a graph Laplacian? Okay, who knows an eigendecomposition of a matrix? Okay, I try to combine them all in one concept, and then you have a GFT. So first of all, the graph Laplacian. The graph Laplacian, in a way, it's this. It's defined like this. It's a degree matrix minus the adjacency matrix. Now, why is this special or good? Or it's basically a second order derivative representation of your graph. Okay. It's only a minor tweak in a way of the adjacency matrix, right? You just put the adjacency matrix in negative, and on the diagonal you put the degree. Okay, so it's nothing very special. If you construct this Laplacian and you multiply it with a graph signal that is constant, by this trick you get zeros. You get all zeros. So that should give you a sense that it works like a derivative. Okay, because something that is constant, so that is not moving a lot, gives you zeros. And you can actually show that if you have a signal on the graph that is very smooth, and you compute this, you compute this operation, so L times the graph signal, you get very low values. Now what we will do is we will look at the eigendecomposition of the graph Laplacian. And this is defined like this. So it means that you will have a unitary matrix U, which on its columns you put the eigenvectors, and you have a diagonal matrix lambda, where the diagonal elements are the eigenvalues associated to the eigenvectors. If you do this for the structural connectome, just extracted from the HEP, and you plot the eigenvalues, you get something like this. So the eigenvalues, of course, ordered with increasingly. So this is what you get. And so you see that you have, actually you start at 0, and you always have at least one eigenvalue that is 0. And that's again by definition of the Laplacian. It's actually because the constant always will give you zeros, that you have a 0 eigenvalue as well. If you have more than one eigenvalue that is 0, it means your graph is disconnected. So usually, at least for the structural connectome, this is not the case. So we only have one eigenvector that is has an eigenvalue 0. And then the next one has already a slightly non-zero positive eigenvalue. And you see then they increase, and since here we also took a normalized adjacency matrix, basically this can never exceed 2, but it basically stops at about 1.5 for the empirical structural connectome we have. So let me show you the eigenvectors, okay, because maybe they are a bit mysterious so far, and they are actually quite intuitive. So this is the eigenvector related to the zero eigenvalue, which is representing this constant I just referred to. And now if you look at the first non-zero eigenvalue and the associated eigenvector, you get this. So it has the size of the nodes is the amplitude of the value in the eigenvector, and the color is either red for positive and blue for negative. So you can see that there is kind of an emphasis on the posterior regions in the brain, and you clearly see that there is a polarity that refers to left-right. And this automatically comes out as from the structure of the connector. It's kind of the most fundamental geometric mode from a topological point of view that comes out of this eigendecomposition, without, of course, the eigendecomposition knowing anything about the location of a region, about actually what it means. It's just driven by the connectivity that is captured in the structural connector, and then revisualized on the brain view. If I look at the next one, very nice, symmetric. Now the polarity is coding anterior-posterior, and it has an emphasis on these two parts of the brain, where let's say the middle regions have a lower value. And I can go to yet the next one. So here you see like a mixture. It has more of the central regions, like central sulcus, but it still has a left-right polarity. So it starts to combine, let's refer to them geometric features, right? But it's basically building up from the knowledge of the structural connectome what you could think of as the equivalent of a Fourier transform. Because these are basically harmonics of the brain, given the structural information. And as you will go to higher and higher eigenvectors, in terms of their eigenvalues that increase, they will basically oscillate faster and faster on the brain graph, on the brain. So that's why we say that the eigenvalue has an interpretation as a frequency of the graph Fourier transform. And the eigenvector is the basis function. So if you actually do this whole thing on a chain graph, you get a discrete Fourier transform, or the equivalent of a discrete Fourier transform. And the eigenvalues will be the frequencies that will be nicely spaced, just like in a DFT. And the eigenvectors will be the exponentials, the complex exponentials. So you can go back to the good old discrete Fourier transform if you like. Of course, you don't need this complex theory then, but the nice thing is now you can do it on a brain. Okay, there is one caveat, and I like to show it anyway. It kind of holds throughout the spectrum, so you have actually nice eigenvectors almost up to the end, but towards the end you have a couple of what I will refer to pathological eigenvectors. Okay, for instance, the last one looks like this. Why is it pathological? Because it's very localized. Okay, and if I'm thinking about the Fourier mode, it's not localized at all. A Fourier mode is everywhere, right? A complex exponential is not localized. So this happens basically when the regularity of the graph at some point breaks down. It's also related to the eigengap and concepts like that. Luckily for us, for the structural connectome of the human brain, this only happens at the very end of the eigendecomposition. And basically for all the operations we will do, it doesn't play a role. But if this would happen very early in the eigendecomposition, we have a problem. And basically then it means you can forget about the interpretation as a Fourier transform. Okay, but for us it's fine. Okay, so why do we need to define a GFT? Because we will use it to do so-called spectral filtering. Okay, so what is it? So imagine you have a graph signal, which is brain activity at a given time point, measured, extracted from fMRI. So it's a vector S, length n. What I will do with this vector is I will compute with the GFT its spectral representation. The way you do this is you pre-multiply S with the transpose of U. And U is this matrix with the columns filled by the eigenvectors in the right order, so increasing eigenvalues associated to it. And then we have another vector coming out, still length S, of course, which is S hat, and which contains the graph spectral coefficients of this graph signal. Now we can do spectral filtering, which means that you take S hat and you will just weight each spectral coefficient, which means you pre-multiply it with a diagonal matrix, H tilde, and H tilde is defined by its diagonal elements, and this is basically referred to as the spectral window that you apply that defines your filtering step. Okay? So you get S hat filtered. And of course, we want to get back in the original domain. So we do the inverse GFT, which means we need to pre-multiply S hat filtered with U to recombine them with the basis vectors. And this gives us the graph signal S filtered according to the definition of the spectral window that we have used. This is actually the equivalent of what you might know as the convolution theorem. If you do a convolution in the time domain, you can go in Fourier, you multiply each of the Fourier coefficients and you get back. And convolution theorem tells you that you have implemented the convolution in the Fourier domain. It is kind of equivalent, as you see, I mean, it's the same intuition. There's just one thing to keep in mind. So, for a general graph, the graph domain equivalent of this operation is actually a shift variant filtering operation. Because the real issue with graphs is how do you define shifts, right? If I give you a signal on a graph, and now this signal I want to shift it around, how do you do that? Okay, if it's a regular graph like a chain graph, you know how to do it. You just shift it to the next node and it's like you get back to the DFT, etc. But in a general graph, it doesn't work like this. And that's why we go into the spectral domain. We define filters by their spectral window. And as you can see here by this little derivation over here, this is actually a full matrix that contains on its rows all the impulse responses that you have applied in the graph domain. And these rows will not be shifted versions of one another. It's not a Toeplitz matrix if you have a one-dimensional equivalent in mind. And so it's very, I mean, you can look at it, of course, if you're interested in a specific graph. But it is really, it's really here that you can do things simple, and the equivalent in the graph domain can be actually very complicated. That's the bottom line. And that's why we do the whole effort of defining a GFT and defining our operations of filtering in the spectral domain to start with, because we wouldn't actually know how to easily do that in the graph domain at all. Okay? Okay, so then we have basically all ingredients now to start playing. So the first thing I like to show is the graph energy spectral density. So what we're going to do is we have our fMRI signals, all the graph signals, right? So for each time point we have a graph signal, and we're going to compute, so it depends on t, on time, we're going to compute the spectral coefficients. We're going to look at the energy of them, so we square them, and then we're going to average this over time. And we could also average it over subjects. So this is the input data, and if you do this operation, you get something like this. And here I've plotted it as a function of lambda in log-log. And actually we looked at the variability across subjects to put the margin over here. So it's minimum maximum, in fact. It's really the full range over all the subjects. So what you can see is that you see a power law-ish regime, right? So it's logarithmic scale. So clearly you have a lot more of energy in the eigenvectors, captured by the eigenvectors with low eigenvalues. Low eigenvalues means low graph frequencies. So smooth signals on the graph. So in other words, fMRI signals, they mostly need to be expressed. They need these low frequency graph eigenvectors. Okay. And then you see that as you go to higher graph frequencies, you have less and less energy on them. So it's a kind of a power law behavior, which, by the way, is not for granted. Who knows how function is actually using structure with respect to this measure? So the fact that it's a power law and dominated by low frequencies, it may be logical, but it's not for granted. Okay, so the next thing we will introduce, again playing with these basic ingredients, is a randomization method. And it's important because we need to have a tool that allows us to knock out effect of structure, effect of function, as you will see in a moment. So what we will do is we introduce the concept of surrogate graph signals, which, as you might know from non-parametric, like permutation testing and things like that, it's basically all the same concept. So you want to randomize something in your empirical data. And once you have randomized it, you will use that to constitute a null hypothesis distribution. So let's get concrete. So what we want to do is, given our empirical functional signals, so our graph signals, we want to generate random signals, surrogate data, but that has the same graph correlation structure. Or in other words, that has the same graph smoothness. So how do you do that? Very simple. Do you know Fourier phase randomization? No? Well, there is a famous method. It's cited 10,000 times or more. So you should maybe look it up once. If you have a time course and you want to, you have a time course and it's kind of smooth. And you want to have other time courses that are as smooth as the one you have measured, but random. One very popular method to come up with those surrogate time courses is to take the time course, compute the discrete Fourier transform, you have the Fourier coefficients, you randomize the phases, you do the inverse Fourier transform, and that's basically a surrogate version of your empirical time course. And you can do that many, many, many times, and you have a family of surrogates. And that's called the Fourier phase randomization methods. Now, we don't have a phase in the sense of a complex phase in our GFT because everything is real valued, but we can still randomize the sign of the spectral coefficients, which actually plays which plays the role of a poor man's phase, if you like. So what we're going to do is we take a graph signal, we compute the spectral version of it, just as before, and now we generate a surrogate spectral version of it by pre-multiplying it with the diagonal matrix, where on the diagonal we just have random +1, -1. So we randomize the sign of the spectral coefficients. We don't touch the amplitude. Okay? We don't want to touch the amplitude because if in the empirical signal we have strong amplitudes, we want to keep them strong. If they are low, we want to keep them low. Okay? And then we get back, so inverse GFT, and we get the surrogate graph signal reconstructed, if you like. And of course, you can now do that many times. Well, by construction, the energy spectral density between the empirical and the surrogate signal is the same, because the spectral density is insensitive to the sign of the spectral coefficients. So that's by construction. The smoothness, as measured by the quadratic form of the graph Laplacian, and that's actually defined like this. It's a very popular way of measuring smoothness. So what you basically do, this is a scalar, you do the transpose of a graph signal times the Laplacian times the graph signal, yes, So this gives a scalar. If I now plug in the eigendecomposition of the Laplacian in this formula, I can actually identify here the spectral forms of my graph signal. And now I can rewrite this as a sum where I have a weighting of my energy of my graph spectral coefficients by the eigenvalues of the Laplacian. And I can, if I do this on the empirical or on the surrogate signal, I get the same. Because again, I only depend on the square of the spectral coefficient, so it doesn't matter if it has been multiplied with plus or minus 1. So by construction, the graph smoothness of all surrogates I can generate will be the same as the empirical signal. Okay. So it's a kind of a strong null model. These graph signals, they look realistic in terms of smoothness, right? Because they have, by construction, the same smoothness as the empirical ones. Okay, so you can think of it like this in total. So you have now your fMRI data. You take a graph signal for a time point. You compute the spectral representation as het. You do the randomization of the signs. So it gives you the spectral form of the surrogate data. And you get back. And if you now do this for every well, you first of all, you can do this many times, okay, with different randomizations. So that's meant by this cycle here. And then you can also do this for different time points. Now, the way we want to apply this is that we apply to different time points actually the same randomization matrix. Why do we do that? Because we don't want to touch the temporal correlation structure. And this is a very simple proof of this. So if you use the same P matrix for each time point, and now you look at S is the data matrix with all the graph signals in its columns, and this is the surrogate data matrix. If I now look at the S surrogate transpose times S surrogate, which is a matrix of number of time points times number of time points. So I'm looking at basically correlation between time points, right? I compute this for the surrogate data. I just plug in this equation, and because I have a unitary matrix, there is a U transpose U that is becoming identity. And so what you see is something like this here, where basically you have a P squared. Now P squared means that if you have a -1, it becomes a +1, and a +1 stays a +1. So this quantity here, which is the temporal, which is characterizing the temporal correlation structure, is unmodified by doing this type of surrogate generation method where you have the same randomization for each time point. So that's the main reason why we keep P constant as we run over the data. Okay, one more thing. As I said, okay, we want to have tools to knock out influence of structure, influence of function. So knocking out influence of function, we do this with this surrogate data generation. Because it gives us random data, but random data that is realistic in terms of smoothness, but it's still random data. If we want to knock out the influence of structure, we need to do something with the adjacency matrix, right? And so what we chose to do, and there are different options here, is to go for the configuration model. So basically, here you have the empirical structural connectivity, so the original adjacency matrix. And we're going to, from the degree matrix only, we're going to have to constitute a configuration model, which is given by this, which is basically an outer product of the degree vector. Okay. Actually, it looks like this, and it's if you like, it keeps the same degree for your nodes, but it redistributes the connectivity evenly to all other nodes. So any preferential connectivity is destroyed, but the degree distribution by construction is maintained. So a node that has many high connectivity, so high degree, still has a high degree in the configuration model. But of course, if this node has many connections to a specific other node, this will be destroyed. So this high degree will be evenly distributed to all other nodes. Okay, so you get the idea. So this is kind of destroying the structure, but keeping the degree distribution, which we know is a very important thing to satisfy, actually. If you destroy the degree distribution, there are so many other things that break down that it's very hard to, well, it's actually too strong as a random model, if you like. Okay, so a simple thing you can do now is to compute, nevertheless, functional connectivity, okay? Not to build a graph model, but just as a measure. And this is what you get, actually. So if you get for original empirical data, functional connectivity looks like this. If you compute it from the surrogate data generated using the empirical structural connectome, it looks like this. And if you compute functional connectivity from surrogate data but generated using the configuration model, you get something like this. So what does this mean? Okay. So if you actually look at the connection-wise correlation between structural connectivity and these different versions of functional connectivity, you get the lowest correlation between structural connectivity and the FC on the configuration model, which is no surprise, right? We have destroyed function and we have destroyed structure. And we get a correlation of 0.3. So functional connectivity from surrogates that ignore structure do not resemble structural connectivity, or not a lot. There is still the degree distribution that influences a little bit, but that's it. If you look at the functional connectivity from the surrogates that honor the structural connectome, we have a correlation of 0.65. And that's actually the highest one among the three. So in other words, this functional connectivity looks most like the structural connectivity. So in this case, we have honored the structural connectome when we generate the surrogates, but of course they are still surrogates, so they are still random functional data. And if you look at what we get for the empirical data, in that case we have a correlation of 0.41, so it is in between those two cases, which kind of means that functional connectivity, empirical functional connectivity, and thus also fMRI signals that are behind it, if you summarize them into functional connectivity, they are not as resembling structural connectivity as they could. Okay, because if I look at my surrogate data, it's actually more like structural connectivity. So the functional connectivity seems to be detached in a way, according to this measure, from the structural connectome, at least to some degree. Okay, and it's not as close to structural connectivity as we might expect. Okay, so actually, and if you think more about this, it means that true functional, empirical functional data is exploiting some interactions between the modes of the structural connectome. And the interactions are exactly what we destroy with the randomization procedure. Okay, we can discuss about this later on. Okay, so now we're going to do some filtering. And the way we're going to do this is we look again at the energy spectral density. Here it is. And we look at the average across all subjects. And we're going to define a cutoff such that we have, on average, equal energy in the first n eigenvectors captured by the first n eigenvectors of the connectome, and then the subsequent ones. And actually, given that we have a power law, you need to take about the first 30 eigenmodes, and that, in terms of the energy in the fMRI, is equal to the next 330 eigenmodes. Okay, so that's about the ratio you can think of. And so once we have defined this cutoff, we will define an ideal low-pass and an ideal high-pass filtering operation. Very simple. So we look at our fMRI signal, we go in the spectral representation, and now we're going to filter with the diagonal matrix F that contains the spectral window, and that will just be ones up to the cutoff and then zeros for the low pass filter and the other way around for the high pass filter. So here we get the graph signal, spectral representation, filtered version, reconstruction. And you do this for each time point. And you can actually see visually that it looks a bit smoother, right? Just by the visualization of the graph signals here in the resulting matrix. And now you can do the same thing with the high pass, and this is what you get, and you see that it looks like more high pass. Okay, because you have removed the low pass, and then you basically see the salient features in terms of graph smoothness popping up. Okay, so what we're going to do with those two filtered versions of our functional signals is to compute the structural decoupling index. And that we define as the ratio of the energy that is liberal or high pass versus aligned or low pass. And we can do that in each node. Because let's maybe first look here. So we have an incoming graph signal. This is the complete filtering, and we call this the aligned version of it, and we can do the liberal as well. So this is low pass, this is high pass. And what we're going to do is we're going to just compute the average energy in a given node over all time points and compute the ratio of liberal versus aligned energy. And we define this as the decoupling index. So what is the intuition? Low frequency eigenvectors by construction capture smooth variations on the brain graph. High frequency eigenvectors capture more salient, less smooth variations on the brain graph. So we make the assumption, given also that the fMRI as expressed on the structural connectome spectral definition has a power law, that if you have more energy in the low frequency eigenvectors, that means your function is more aligned to the structure. Okay, it's kind of easier to express a low frequency pattern on the structural connectome. While if you need a lot of liberal energy, it means that it's complicated. It's not something that is easy to express on the given structural connectome because it's at the high frequencies. Okay, it's not something that is the first natural expression given the connectivity of the graph, of the brain graph. So that's the intuition. So we just look at the ratio of these two types of energies. And then you can compare it, you can compute it for empirical data, but you can also compute it for surrogate data on the empirical connectome or for surrogate data on the configuration model, derived from the empirical connectome. And this is what you get. So here we start again with the surrogate data generated on the configuration model, and they're all in the same color range. So this is the logarithm of the decoupling matrix, decoupling index. So 1 means a doubling of decoupling energy, so decoupled, and -1 means half, so coupled between function and structure. So what you see here is that this is very red. So surrogate data that is generated by a configuration model, so that doesn't take into account the real structural connectivity, is actually, in terms of the decoupling index, very much decoupled from the true structure, right? Because the decoupling index is always computed with respect to the true structural connectome, of course. So which makes perfect sense. We have surrogate data that doesn't respect structure, so it's decoupled. If you have surrogate data that does respect structure, you get a picture like this. So it's much more nuanced now. And you see that you have blue coming up, which means that there are regions that are more coupled than you basically would expect. Okay? That have more aligned energy than liberal one. So there is a redistribution in the brain given these signals, between coupling and decoupling. And you see that the regions that are more blue, they're mostly in the sensory regions. We have visual occipital, we have central sulcus, we have auditory cortex. And then we have some reddish type of nodes, which are prefrontal, temporal pole, and there are some in parietal as well, if you look closer. So this is surrogate data, so random data, but honoring the true structure. And now if you look at the empirical data, the truly empirical data, it's actually a similar pattern to this, but stronger. Okay. So the strength of the coupling is even more pronounced than in the surrogate data, and the strength of the decoupling is also more pronounced. And you can actually do statistical testing to prove to what extent this will survive a null hypothesis made up by the realistic null data. Okay, that's one of the reasons, of course, we can do this many, many times and then do statistical testing. But the interesting thing, if you take this result here and you now order the nodes according to the decoupling index, that reveals a gradient in the brain that if you link it with a metadata database, so like Neurosynth, which is summarizing task fMRI results of thousands of studies, and you can basically put in a set of nodes that is in a certain percentile of the decoupling index, and then you can link to which topics in Neurosynth are most expressed for these nodes, given all these studies in the literature. You see that the gradient of coupling to decoupling corresponds to a behavioral gradient that goes from low-level processing to high-level processing. And this is very similar to a result you might know by Daniel Margulies, where he used the connectivity on the cortex, the functional connectivity on the cortex, to come up also with the gradient, which gave him a very similar low to high level cognitive behavioral link. But in this case, we get it from a completely different type of measure, which is the structural decoupling index. So how close, in a way, is the functional expression to the structural connector? Okay, so to conclude, let me just... So what you will do in the brain hack with Thomas in a moment is playing with these tools, okay, and trying to get a handle of how you compute the eigendecomposition and how you filter and how you can generate a surrogate, etc. And in a way, I hope you get this by now. It's really just a very fundamental tool, right? It's even not a full pipeline. It's just ingredients that you can assemble and put together in many different ways, depending on the question you like to address. So, and I hope you like it to play with in the future. What I would like to show you to conclude is some ongoing work in the lab that you won't be able to do during the brain hack because computationally it's a bit more heavy, but it's actually responding partially to Cézanne's question, which is, can we get rid of the atlas? And so the atlas is very nice. I mean, the 360 atlas is not too bad, to be honest, but it's still an atlas. And if you go to layered, it's certainly not adequate. So this is just one attempt to go to a voxel level brain graph. And the way we do this is we consider basically all voxels intracranial, gray matter and white matter. So if you stay at the resolution of the HEP, that gives you about 1 million nodes, a bit less. And we get the local connectivity, so just connectivity between a voxel and its surrounding voxels from the diffusion-weighted measurements. And then what we will do is we have this huge matrix, but which is sparse because we only have local connectivity, so we don't explicitly store it. And we can use large-scale eigensolvers to get at least the leading eigenvectors. And an eigenvector in this brain graph sense is a brain map, because an eigenvector will have 850,000 nodes, and you can visualize it like a map, right? And they look like this. So they're just informed, again, by structural connectivity, and you can see that we get very nice, it basically summarizes the information in the diffusion-weighted MRI measurements, and you see that within the white matter, it kind of discovers tracts, which is no surprise. It's kind of global tractography approach. You can actually link it, very similar to a paper that Matteo showed me once. You can link each eigenmode to tracts, given white matter atlases that exist. And of course, since these are eigenvectors, so it's comparable to principal components analysis, you have orthogonality and so on. So the way these tracts are expressed will be basically linear combinations as you go along. Okay, and actually for those who are interested in the details, we do this in a subject-specific way, and we wanted to know what is kind of the characteristic dimensionality that is shared between subjects. Because we have 1 million nodes, approximately, but that doesn't mean that the amount of information in terms of dimensionality is 1 million. And if you look at the Procrustes transform to match these eigenspaces between subjects, you can get to an estimate of about 300. So maybe the current atlases of 300, 400, 500 nodes, they are not too bad from this perspective. Although these are linear spaces, so they could actually accommodate more nodes than 300, because they are linear combinations and so on. And then it's not a discrete clustering, but okay, that's another thing. So what we do then next for now is we do so-called in-painting. So the idea now is that we get the fMRI, and we measure fMRI on the gray matter. What we measure on the white matter is still debated. Maybe there is a weak form of activity, but certainly not something that is obviously extractable there. So what we do is we get the fMRI, and we only keep it on the gray matter. And then we put this activity on the brain graph, the nodes in the gray matter. And we're going to solve basically a constraint diffusion equation, where we are diffusing given the connectivity of the brain graph, especially in the white matter, and we are constraining that by the activity in the gray matter. Okay? So I call this in-painting. It's, let's say, a biological plausible reconstruction of how activity could look like if you would be able to measure it in the white matter, given the gray matter activity that you do measure. And if you do that for many frames, it looks like this in a movie way. Okay, so on the gray matter is basically fixed by the measurements, and you see that this method has reconstructed something at least in the white matter as you go to different gray matter configurations. So just to try to summarize this a little bit, if you would do simple PCC seed connectivity, so you have a voxelized connectivity map with the time course extracted from the posterior cingulate cortex, if you do this on the original bolt, you get the top result over here. Okay, so you basically get the default mode network, right? If you do this on our in-painted version of this data, you get this. Because of course you can now do this also with white matter voxels, or in other words, the white matter voxels do contain something that is informed by this in-painting process, and thus by the structural connectivity there in this reconstruction process. And you can see that you have at least, without going into too many details, that you have many meaningful tracts that are reconstructed and that support the activation of the default mode network. Okay, in particular, you have the connectivity between the MTL and the PCC and things like that. We can look at it more closely. You have also very nicely the corpus callosum, which of course supports the homologous regions and so on. Okay. So to conclude, so GSP, it's something relatively recent in the signal processing community, and I think there is a potential, an opportunity in neuroimaging. I think it's a rather natural way to try to incorporate structural information into operations you will perform on functional data. It takes into account this backbone in a very nice way, and you can knock out effects of function and structure by these computational tricks like surrogate data, null model, configuration model, and so on. And as I said, it's just basic ingredients of whatever you like to do, right? It's just basic operations in the end. So, for instance, I've mentioned dynamic in the Ignite talk. Well, you can do many types of dynamic analysis with the GSP framework, because for now what I showed you is basically summarizing energy over all time points, but nothing prevents you from keeping the filtered signals time point by time point and doing some things, you know, time point specific. If you have task fMRI, you could look at the specific moments of a task. How does the structure decouple from the, or the function decouples from the structure, for instance? And in which regions does that happen? So it's all open there. There are some challenges, of course. I think that the most important challenge is to give a precise, meaningful interpretation to these operations. And that depends, of course, to what extent you make the framework flexible or not. For instance, to give you one example, if you would make the structural connectome subject-specific, then your definition of the graph Fourier transform becomes subject-specific. So, which means that if you then define a low-pass, high-pass filtering by a fixed cutoff, it means something different for each subject. So how are you going to exactly take that into account in your interpretation? Okay. There are things like this which are not completely resolved. Okay, so it could allow you to have joint modeling of space and time, and then of course future extensions could go to multi-graphs. Maybe if you have layered fMRI to try to take this into account in the modeling as well, etc. And with this, I have nothing more to say, and I give the stage to the master brain hacker of today, Thomas, who will illustrate all this very nicely. Thank you very much.
Is there any question? Dimitri? Which does mean you've been very, very clear, or that your university looks not great? Which language have okay.
Matthias.
Okay.
Very, very nice talking, very well. How much is the result of the GST's kind of framework on the, for example, sampling rate that you have in your fMRI acquisition? Like, does it depend whether it's a 3-second TR, 2-second TR, or do you see any
yeah.
How much depend?
Sorry, before answering, can you repeat the question in the microphone?
Okay. So the question is, how much does the GSP depend on the TR, on the sampling rate? I mean, we didn't investigate because we looked basically at these temporally summarizing measures for now, like computing the energy over time and so on. And I mean, I think it will only start to play a role if temporal features are becoming important. And then maybe you want to go to something which I call joint modeling of space and time. You want to add type of filtering also in the temporal direction. So for now, we don't touch the temporal direction. Actually, as said, we don't want to touch it. We want to maintain, for instance, in the surrogate data generation, all temporal correlation untouched. But perhaps if you would try to match an HRF, or you take into account some smoothness of the HRF, so in the temporal direction, then of course the influence of the TR will become apparent. And yes, but as such, the GSP is a spatial operation. So there is no direct, obvious influence of the temporal properties.
Sure. Would be interesting to try to see with MEG, I guess, and EEG as well, right?
Yeah, you could. Oh yes, you could replace fMRI by EEG, reconstruct it on the atlas, for instance. so with source imaging or MEG, and exactly.
Yeah. And when you were talking about the in-painting regarding the single subject prediction, do you still use the single subject fMRI time series, or do you also average both? Because you do average the structural connector as far as I understand.
So in the big brain graph, so the voxel level, there the structural connectivity is kept at the subject level. So this big eigendecomposition, it is done in the subject space. And it's only when we have the eigenmodes that are maps that we do the procrust test. Because then we can compare basically summarizing modes of these very fine structural connectors. We try to average this with normalization across subjects, and it gives us a voxel level connectome, but it's much more blurry, as you can expect. So visually it's really much nicer if you keep it at the subject level, if you want to do the voxel level brain graph. And that's again, if you go atlasing, it's one of the advantages that you can go in normalization earlier in the pipeline, let's say it like that.
Any other question? Would you rather start now with a tutorial and then half an hour go for a coffee break, or take the suggestion that Vicente is trying to gesticulate to me and then break now and then tutorial after? I guess it's go have a little coffee break now. One question before you go. One question. Yes, exactly. Is there anyone that wants to have a tour of the labs downstairs?
What?
Can you please raise your hand if you want to do it?